Let's explore the important topic of page size considerations in virtual memory systems. This is about understanding the trade-offs involved in selecting the right page sizes. We will discuss how different page sizes, whether small or large, affect the performance and efficiency of memory management in our computers. We will cover three main areas: the comparison between small and large pages, the performance trade-offs that come with each size, and how these sizes influence memory management efficiency. Now let us delve into the key factors that influence our choice of page sizes. On the left, we have small page sizes. Using small page sizes leads to less internal fragmentation, which means memory is more precisely allocated, leading to better memory utilization. It provides a finer granularity for page replacement, optimizing how memory is used per process, and ultimately reduces memory waste. On the right, we have large page sizes. These result in smaller page tables, requiring fewer translation look-aside buffer, or TLB entries. They contribute to better spatial locality, meaning data that is used together is stored together, reducing page faults for sequential data access. Large page sizes also lower overhead for input-output operations. Now, let us take a look at a visual comparison of how different page sizes affect memory organization. On the left, we have small pages, which are 4 kilobytes. With small pages, there are more page table entries but less internal fragmentation. In the middle, we have medium pages, which are 64 kilobytes. These provide a balanced approach and moderate table size. On the right, we have large pages, which are 2 megabytes. With large pages, there are fewer page table entries but more internal fragmentation. Each column represents a different page size, and the grid within each box visualizes how memory is divided and managed with that particular page size. Here, let's analyze the trade-offs between page size and system performance in a table. We will examine how different page sizes affect internal fragmentation, page table size, TLB efficiency, and input-output efficiency. For a small 4 kilobyte page size, internal fragmentation is minimal at 0.5 to 2%, but the page table size is very large, resulting in lower translation look-aside buffer hit rates and more input-output operations. For 16 kilobytes page size, there is low internal fragmentation of 2 to 5%, and large page table size, with moderate translation look-aside buffer hit rates and moderate input-output. With 64 kilobytes, internal fragmentation is moderate at 5 to 10%, the page table size is moderate, and there are good translation look-aside buffer hit rates and efficient input-output. With a large 2 megabyte page size, internal fragmentation is high at 10 to 30%, the page table size is very small, and there are excellent translation look-aside buffer hit rates and very efficient input-output. Let us explore the mathematical analysis of how page sizes impact memory management. We'll start with the internal fragmentation formula. Internal fragmentation, denoted as if, is calculated by subtracting the memory actually used, or M, from the page size, or P. This formula helps us quantify the amount of wasted memory within a page. On average, the last page of a process wastes half a page. Now, let us consider page table size calculation. For a 64-bit address space with different page sizes, the address space equals 2 to the power of 64 bytes. If the page size is 4 kilobytes or 2 to the power of 12 bytes, the number of pages equals 2 to the power of 64 divided by 2 to the power of 12, which equals 2 to the power of 52. If the page size is 2 megabytes or 2 to the power of 21 bytes, the number of pages equals 2 to the power of 64 divided by 2 to the power of 21, which equals 2 to the power of 43. Increasing page size from 4 kilobytes to 2 megabytes reduces page table entries by a factor of 2 to the power of 9, which is 512 times. Now, let's analyze the performance impact of page size on system performance. We will examine the relationship between page size and system performance using a graph. The graph illustrates the performance trade-offs associated with different page sizes. The horizontal axis represents the page size ranging from 4 kilobytes to 2 megabytes. The vertical axis represents the performance level from low to high. The first line, representing TLB hit rate and input-output efficiency, shows a positive correlation with page size. The second line, representing memory utilization efficiency, displays a negative correlation with page size. Let's consider real-world page size implementations, looking at how different operating systems handle page sizes. Here's a snippet of the Linux kernel code for huge page support, specifically the huge translation look-aside buffer fault function. This code checks if a huge page is available and maps it if it is. Now let's examine a table of page sizes in modern operating systems. For Linux, the default size is 4 kilobytes with large page support for 2 megabytes and 1 gigabyte, which are called huge translation look-aside buffers. For Windows, the default size is 4 kilobytes with large page support for 2 megabytes and 1 gigabyte, called large pages. For macOS, the default size is 4 kilobytes with large page support for 2 megabytes and 1 gigabyte, called super pages. For FreeBSD, the default size is 4 kilobytes with large page support for 2 megabytes and 1 gigabyte, called super pages. Lastly, for Solaris, the default size is 8 kilobytes with support for 4 megabytes and 256 megabytes. Let's review the key takeaways of page size selection. First, let us consider the optimal balance. Most modern systems use a hybrid approach with small base pages of 4 kilobytes and support for larger pages when needed. Second, let us consider workload considerations. Database servers benefit from larger pages due to sequential access patterns, while desktop applications often work better with smaller pages. Third, consider the hardware impact. Translation look-aside buffer size and memory architecture influence optimal page size selection. Larger translation look-aside buffers can better support smaller pages. Lastly, let us look at future trends. Growing memory sizes and improved hardware support for multiple page sizes will continue to influence page size selection strategies. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.